Hello, everyone. So today we are going to be talking about chemical reactivity. So in order to start this conversation, we're going to bring up another famous chemical incident. This one some of you may end up remembering from about 3 years back when Hurricane Harvey plowed right into the Houston area. Well, one of the reasons why this was of great concern to the chemical community is that Houston is one of the biggest areas of oil refining in the world. And right next to those oil refineries are all of the chemical plants that essentially process and manufacture the petrochemicals derived from that oil. So, one of the biggest areas of chemical production happens to be the Houston area. And there was one of the biggest hurricanes ever seen headed straight for it. And one of the most famous incidents of what could happen when a hurricane hits a chemical plant happened just outside of Houston at Crosby, Texas, where the Arkema chemical plant lost power. So essentially, the plant ended up flooding, which took out their cooling, their power generators, including the backup. This was particularly problematic because one of the products that Arkema generates is organic peroxides. It turns out that organic peroxides really don't like room temperature, so much so that they quickly become, well, combustible and highly reactive. So, in the end, they had to remove the organic peroxides to refrigerating trailers that are typically used for chemical transport. And those eventually started losing power. And uh, this resulted in two separate fires where trailers essentially caught flame. And then the remaining trailers had to be destroyed with a controlled burn 3 days after the first fire. All said, all said and done, 21 people were hospitalized, mostly with respiratory conditions, and 200 people were evacuated as the surrounding area within 1.5 miles of the chemical plant needed to be evacuated for approximately a week. So, again, one of the things you need to watch out for when thinking about chemical reactivity is not just what sort of chemicals do you have and what sort of conditions they have, but what sort of entire support network do you need? For example, if you have to, leave your lab for a week because, or even a month because of a pandemic, what sort of materials can't be left alone? And this is really one of the big lessons of Arkema is watching out for what sort of support networks the reactivity of your chemicals may require. So let's go ahead and talk a little bit about the idea of chemical reactivity. So one of the major lessons of chemical reactivity at this more intro point, as you haven't had a lot of organic chemistry yet, is focusing on this idea of what major classes of chemicals should not go together. So what are some big flags of reactions that may end up happening between chemical species? So we're going to go ahead and first walk through this by talking about some of the major uh, classes of chemicals and what sort of reactions they're well known to have and what sort of dangers they might pose. So let's start with a familiar category, our good old friend, the acids. So this is, again, usually referred to as a Bronsted acid, so that's going to be any proton donor. So classic friend here is HCl. And one of the things you have to watch out for is that most acids can essentially slowly erode metals. So this is a reaction that's kind of famous with zinc, but it happens much more slowly with other metal species. Where if you mix HCl with zinc and add a little bit of heat to make it go fast, what you're going to end up doing is reducing the zinc, or oxidizing the zinc to make zinc chloride and reducing the hydrogen to make H2. So you may have seen this as a classic demo reaction where the hydrogen can then be ignited on fire. But again, this is just a example case of a reaction that happens in general with most metal species when combined under acidic conditions, is it's possible to essentially erode them by making an aqueous complex. Other things that people tend to worry about with acids is their reaction with organic tissues. So a good example of this may be, say, the interaction of acids with, say, amines. You know, the good old building blocks of proteins. So this includes an amide bond. It turns out that if you expose an amide bond to a strongly acidic conditions, you can essentially cleave the amide to make a organic acid and an amine, which unfortunately means you just ate through your proteins. Interestingly enough, this is also part of the preservation method of pickling meat or just heat treating or acid treating meat. So if you enjoy your lutefisk, say hello to how it happens. Then we also have bases. So this is again a class of reactions we're often aware of, where you may have things like your classic hydroxide, say sodium hydroxide, which can interact with, say, fats. And this reaction is called saponification, where you react sodium hydroxide with, say, a triglyceride. So this is the building block of most fatty tissues, which essentially is composed of an ester. Well, it turns out that the hydroxide can cleave this ester to make a deprotonated fatty acid and an alcohol. Unfortunately, at this point, what you've done is you've just turned your fats into soap. Thus, this reaction is called saponification. Turns out that your body has a lot of fats and especially sensitive tissues like your eyes. Please do not get sodium hydroxide in your eyes. But it's also worth noting that bases like sodium hydroxide can also react with, say, proteins for, again, degradation reactions, as well as the famous case of what happens when I mix an acid and a base, which essentially ends up with proton transfer and a whole lot of heat. The whole lot of heat is usually the big worry there. Then we have organics. So this is, again, your classic carbon-rich species. And I'm not going to get too much into the specific dangers of things like halogenated organics, which tend to have more toxic issues. But in terms of reactivity, one of the biggest dangers of organics is they tend to make very good fuels. And this means that they're very vulnerable to exposure to oxidizing agents. And so there's a whole slew of oxidizing agents out there, including a lot of peroxides and species like chlorine and bromine. But one of the most frequent oxidizers you're going to have to watch out for is nitrates. And a great example can actually be shown with nitric acid, which unfortunately is actually a fairly powerful oxidizing agent, as you can see through its reaction with toluene. Because it turns out, when you react toluene with nitric acid and a little bit of help, what you can end up producing is trinitrotoluene, more commonly known as TNT. It turns out that most of the products of a reaction in between nitro groups and organics tend to produce nitrated organics, which essentially are fuels that take their oxidizing agent with them. Thus the reason they're so commonly used in explosives. And just to make it fun, this reactions of organics and nitrate groups tend to also produce a fair bit of heat. So, who doesn't like mixing heat and explosives? Thus, one of the most common warnings you will ever receive is to be very aware to not mix any of your acids with any organic waste. So we'll often be very, very cautious of keeping any nitrogen-containing compound away from organic waste, because there has been more than a handful of waste bottles that have been known to explode because somebody accidentally did some variant of this reaction of mixing an oxidizer with an organic. On the opposite end of oxidizers, we have reducing agents. The most powerful reducing agents are often called water reactives, and they do so because they undergo quite potent chemical reactions with water. So let's go ahead and talk about that butyl lithium that I was talking about earlier. So this is essentially just a butane group where I replaced one of the hydrogens with a lithium, which means effectively it's a carboanion. So I've got a negative charge on a carbon, which frankly really hates it. So another way of thinking of some of these water reactives or highly reducing agents is these may be the most potent bases you've ever seen, and they'll rip a proton straight off of water. But it turns out they'll do it with so much heat that you can actually ignite the butane you just made. So it is not uncommon for some reducing agents to be pyrophorics, where they will literally catch fire when exposed to water or air, which can be, well, quite dangerous. Now, one of the things you have to watch out for is actually something you often don't think about, which is aqueous species. Now, sometimes the reactivity danger of aqueous species might be what it actually contains. For example, you can imagine water containing a lot of oxidizers, some reducing agents, bases, or acids. But sometimes the danger is actually, as we just saw, with the water itself. Because it turns out that water's a bit of an oxidizing agent. Not a good one, but it is an oxidizing agent, which means it can reduce with strong reducing agents. Turns out that water is also kind of a crappy reducing agent, which means it can react with strong oxidizers. By the way, it turns out that water is also a very weak acid or weak base, so it turns out that it can react with strong acids or bases. If you don't believe me, see what happens when you react sulfuric acid, a very strong acid, with water. The answer is that if you're not careful, this reaction can break glass. It is that hot and that reactive. So remember, do as you order, add acid to water. Essentially, this is a way to make sure the reaction occurs slowly if I add very small amounts of acid to the more dilute water. If I try and add the dilute water to the strong acid, all the water will immediately react, producing a lot more heat and a lot more splatter. And again, be very cautious when adding water to an unknown species, because again, these reactions can be a lot more energetic than you think. And this is also one of the reasons why I'm going to be spending a little bit time later about talking about why it's so incredibly important that you go ahead and make sure you separate your waste to help separate any potential reactive species. One of the other things you also need to watch out for is that it turns out that a lot of chemicals don't belong to a single reactivity group. A lot of them will belong to two or more. For example, an aqueous base is going to behave very differently from an organic base. Similarly, you have plenty of species like nitric acid, which is an aqueous oxidizing acid. And you have to treat each of these dangers independently. For example, nitric acid, in addition to just being an oxidizing agent, can also do things like erode organic tissues and dissolve some metal surfaces. So again, watch out that you're paying attention to all of the chemicals' dangers. And again, if you need essentially a good guide of what chemicals to keep the heck away from other chemicals, you can often make use of one of any number of charts, and you're going to tend to see certain trends hold. So, for example, certain species you can see mixed, and those are going to you can mix together. And you're going to see those with essentially open spaces, and you'll notice any chemical should be able to mix with somebody of its exact same category. And let's go ahead and talk about our our oxidizing acids, like nitric. Turns out I can tend to mix my oxidizing acids with inorganic acids like HCl, but I'm going to want to keep them away from, say, organic acids like acetic acid, or bases because, well, both of these reactions can tend to be very exothermic and quite dangerous. But in general, if I've got an organic oxidizing agent, it can also mix with other organic or inorganic acids and inorganic oxidizing agents. But again, you may notice not a lot else. We don't know what sort of reactions it may occur with poisons, organic or inorganic. Keep it the heck away from water reactives and most of your classic organic solvents. And again, similarly, you'll might notice that organic acids like acetic acid are pretty much only safe to mix with organic solvents. And if I have, say, a nice good base like sodium hydroxide, as long as it isn't an oxidizing agent, I can tend to mix these with a lot of oxidizers or poisons. But again, make sure that just if you have an aqueous waste that contains oxidizers, make sure it does not contain both bases and acids. Otherwise, tears and large amount of heat and potentially danger may end up happening. And you're going to see a lot of these major themes. A lot of the who can be next to who is going to be driven by acids have to stay away from bases, oxidizing agents have to stay away from organic species, and water reactives. So again, hopefully this gives you a good guide of what you should watch out for when you're wandering around a lab. Make sure that you do not place any of these unfortunate chemicals next to each other. And if you see a shelf or a tray that contains any of these species in close proximity, please let your instructor know as soon as possible, because A, something was probably misplaced, and B, there may be potential danger that results. So please try and be very aware of who can be next to whom. And again, this has a lot to do with what chemicals can be next to what other chemicals, but it isn't always enough to know which chemicals are compatible. It's also very important that you know which chemicals may be compatible with certain containers. For example, let's say I have a good acid like HCl. It turns out that I probably don't want to put this inside of any metal container because, well, it can indeed corrode my metals. It can also have some unfortunate interactions with classic organic tissues, but this can include things like certain adhesives and maybe even other certain organic polymers. Again, when you're choosing a bottle that can a plastic bottle to contain acid, make sure that you're very aware of what type of plastic you're using and what its compatibility with any given type of acid might be, because these may be more problematic than you think. Similarly, another thing you have to watch out for is going to be amines. So amines are actually quite problematic because they're good ligands. In other words, they can readily bind to metal ions, which means they're really effective at corroding metals. So again, try and keep any metal container or even metal fixings away from any sort of amine solvents. Similarly, be very cautious of when you're packaging your organic solvents or organic products, because turns out that organics like to dissolve like, and most plastics are, well, nonpolar too. So it is not uncommon for organics, especially chlorinated organics, to like to dissolve plastics and some rubber species. So again, be very cautious. Organic solvents, depending on what you're working with, may need to be contained in more glass or ceramic containers. And again, similarly, watch out when handling peroxides. They love to dissolve organic tissue because nom nom, and they may be reactive with some types of metals, mostly because peroxides are weak oxidizing agents. And again, whenever you're choosing a storage container, make sure that you are very aware of what material it's made of and what sort of species it may react with more than others. And in case you're curious, I put a full list of corrosive interactions between some of the most common sets of chemicals and most common materials up on Blackboard. And this can be a very useful list in trying to determine what potential reactions may occur. So next time, we're going to be talking a little bit more about how to identify chemical dangers. Till then, take care.